So you want me to share my screen? Share my screen?
Yes, please. So it's my pleasure to introduce our second speaker, Jimmy McLaughlin. He has the first person I have met who was older than his PhD advisor. And he'll be speaking to us today on some remarks on the coefficients of Hecke eigenforms and Chebyshev polynomials of the second kind. So go ahead, Jimmy.
All right, thanks, John. I was looking back over my slides folder, and I saw I'd first been at West Coast Number Theory in 2001 with my advisor, Doug Bowman. And I haven't been there very often. I was there maybe 3 or 4 years ago before pandemic, when it was at the Lighthouse place. But hopefully I'll get back there in person again soon. All right, so here's just a brief overview of the course of this talk. I'm going to say a little bit about background and notation. In the background, I'm going to talk a little bit about work that led to what's in this talk. It's sort of connected. And then, since it's a lot about Chebyshev polynomials of the second kind, I'm going to review their properties. And then I'll see what implications they have for the coefficients of Hecke eigenforms. So a little bit of notation first. I'm not sure how much people know of this stuff, so I'm going to go through it. For q less than 1 in absolute value, the usual infinite product qq sub infinity is 1 minus q times 1 minus q squared times 1 minus q, etc. And an abbreviated notation just to make things easier to read. For that product, I'm going to use f sub 1. And then if I replace q by q to the j in that product, I'm going to use f sub j. And I'm going to be talking about products whose series expansion is lacunary. So just the definition of that. Essentially, it just means most of the coefficients are 0 in this precise sense. And sorry, something's okay. Here we go. So a result of Serre, fairly well known, is that for even positive integers s, f1 to the power s is lacunary if and only if s is one of these integers here. And another definition, an eta quotient is a finite product of the form f sub j to the power n sub j for some positive integers j and possibly negative integers or positive integers m sub j. All right, so I want to introduce this by recalling a result of Han and Ono. So we're going to consider that f1 to the power 8, that was one of the powers considered by Serre. And so suppose that series is a sub n q to the n. And suppose now we look at this other eta quotient here, f sub 3 cubed over f sub 1. And suppose its coefficients are b of n. Well, then Han and Ono proved in 2011 that these coefficients vanish in the same places. A sub n is 0 if and only if b sub n is 0. And moreover, they give a precise definition of when when each of these vanished. It's for non-negative integers n for which the order of 3n plus 1 of p is odd for some prime congruent to 2 mod 3. All right, so some such prime then occurs in the factorization of 3n plus 1 to an odd power. If that happens, then these coefficients up here vanish. All right, so just another bit of notation here. If a of q and b of q are two functions for which the coefficients in the series expansion satisfy that condition, then we say the coefficients vanish identically, or that these two functions have identically vanishing coefficients. All right, so Han and Ono's theorem, when I came across it, sort of motivated me to investigate experimentally if similar results held for other pairs of eta quotients. And so what I discovered experimentally can be summarized as follows. If A of Q and B of Q are any one of the pairs in this list, then if we define the sequences A of n and B of n to be the series expansions of these two functions, then A of n is 0 if and only if B of n is 0. And we can give similarly precise criterion for when these coefficients vanish identically. All right, now for this pair, we don't have an if and only if condition. They're both 0 if 12n plus 13 satisfies a criterion of Serre for the vanishing of A of n. Now, I had done some work on vanishing coefficients in infinite products before, but they were all vanished in arithmetic progressions and it was pretty easy. Now, this needed the theory of modular forms, and so I didn't know at the time how to prove these things, so I did what I usually did, which was email a group of people I went to grad school with and published with, keep loosely in contact with them to ask them. And Tim Kuber, okay. Tim Kuber asked if he could contact a collaborator of his, Dongxi, and he did, and eventually we were able to prove all these results. Now, just an aside before moving on, we're still investigating this situation, and it appears that these results up here are just the tip of an iceberg. So, for example, if you consider like f1 to the 6, we've discovered like something like 150 products that have the same property, the coefficients either vanishing identically, or there's this kind of a tree structure. There are some of them who vanish in the same place as f1 to the 6, but vanish in additional places, and we don't know how far up this tree goes. Anyways, so I want to just give a brief outline of how we prove these things. So we apply a dilation to the eta quotient, q to the q to the m, and multiply by an appropriate power of q to the j to turn it into a modular form. And then because of a result of Serre and lacunary forms, we were able to experimentally express these as a linear combination of CM forms, and then using the storm bound, verify the equality. And then using the result of Rubit, we were able to express these CM forms as linear combination of theta series. And because these quadratic forms only have finitely many representations for primes, we were able to get precise explicit forms for the coefficients at P. And then we use the multiplicity of the coefficients in the CM forms and the recursive formula for prime forms, prime powers, more on that later, to get information generally about the B sub n, and in particular when they're 0. All right, so what's the connection to work in the previous, or work in the present talk? Well, recall that this was only a one-way direction. It wasn't an if and only if. Well, initially I mistranslated Serre's criterion as an if and only if, and I was trying to prove both directions and try to prove that possibly false result led me to the criterion in the next few slides, or the result in the next few slides. So first of all, recall Chebyshev polynomials of the second kind. They're defined, as you see here, for u of 0 and u of 1, and then recursively by this recursive relation. And now what we found was that if f of q is a normalized Hecke eigenform, and suppose this is the recurrence relation at prime powers, then we have this formula for the coefficient at p to the n in terms of the coefficient at p. It's namely a certain expression involved in the nth Chebyshev polynomial. Now, so the thing is like, well, I'm going to skip the proof here, but it's fairly simple. You just show that they satisfy the same recurrence relation and same initial values and so on. The thing is that, well, asking around, it seemed like it was known to experts like Dongxi and Ken Ono and Larry Rolen actually gave me a reference, but it was stated somewhat obliquely. And so since it seemed to be not well known, we decided to write a short paper on it. Now, the thing is that you can use all the identities you have for Chebyshev polynomials of the second kind to get results about these coefficients in these Hecke eigenforms. All right, so let's just briefly then scroll through some of these properties of the Chebyshev polynomials of the second kind. All right, so the generating function, these are all well known. Here's the explicit closed form. There are various identities connecting. Here's an explicit form as a polynomial. Here's something, a connection. Now, T sub n, I should say, is the Chebyshev polynomial of the first kind. And I notice here that we have this result that if n plus 1 divides m plus 1, then u sub n of x divides u sub m of x. And then various other identities that I'm not going to spend too much time on. I do want to mention the exponential generating function.
You have 5 minutes remaining.
Okay, here's a simpler version of that. And here are some other ones. And now here are two bivariate generating functions. So we have two Chebyshev polynomials with different arguments. And here's the ordinary generating function for these. All right, so in the last few minutes then, I just want to say what we can get then applying those identities for the Chebyshev polynomials. All right, so we use this connection between the a sub p to the n and the Chebyshev polynomials then. Now, I'm going to illustrate these identities using the Ramanujan tau function, and that's the 24th power of f sub 1 multiplied by q. And just to recall then that these coefficients satisfy the multiplicative property. And so, for example, if you multiply t of 3 and t of 5 together, you get t of 15. And they also satisfy this recursive relation of prime powers. And again, here's an illustration of that for p being 2. All right, so this is a well-known thing. I mean, the L function, we can derive this is another way of deriving it, but I'd rather move on to some results that I think are new. So if we use this identity, then we can get this identity for the square of the coefficients. And this kind of L function for the square of the coefficients is equal to this infinite product. And then here's an example using the Ramanujan tau function. We have this identity for any prime p. And then we have this L function for tau squared. Using the exponential generating function, then we have this general result, and we have this simplified version of the exponential generating function leads to this. And once again, if we illustrate this using the Ramanujan tau function, we have this identity, or the simplified version, we have this. And now if we go back to the bivariate generating functions that I mentioned, we get this general result then for any Hecke eigenform. P1 and P2 are, if they are distinct primes, we get this. And then similarly for the ordinary generating function, bivariate generating function, we get this simpler statement. And once again, illustrating these using the Ramanujan tau function, we get this identity if P1 and P2 are any primes. And of course, simplifies quite a bit if the P1 and P2 are equal. And then if T satisfies this inequality here, then we get this result for P1 and P2. All right, and then one of the other identities I showed you, the one that had the divisibility property. Then for an arbitrary Hecke eigenform, we have this result. Okay, and again, if we illustrated using the Ramanujan tau function, we have this. And to illustrate the divisibility property explicitly, if n plus 1 divides m plus 1 and p is any prime, then we have this divisibility condition. And as an example, if m is 119, and we consider the divisors of p of 120, then for any prime p, t of p to the n divides t of p to the 119 for any n in that set. And that was a bit rushed, so thank you for listening and watching.
Let's thank our speaker.